This is a screen we are all familiar with. You select a network name, a checkmark appears, and you are online. But behind that simple checkmark is a strict technical requirement. To send or receive even a single email, your device needs a digital mailing address, known as an IP address. Without one, the network simply does not know where to deliver your data. In the early days of computing, getting that address was a highly manual task. A network administrator had to physically walk over to each new computer, pull up its settings, and type in a unique string of numbers by hand. In this diagram, we see the primary danger of that manual process. If a tired administrator accidentally types the exact same address into two different devices, the network gets confused, the data collides, and both devices drop offline completely. To remove that risk, engineers created the Dynamic Host Configuration Protocol, or DHCP. Instead of relying on a human with a clipboard, DHCP acts as an automated manager, handing out, tracking, and recycling addresses instantly. By taking over the repetitive work of assigning addresses, DHCP handles the exact tasks where human operators are most likely to make a typo, a mistake, or a duplicate entry. It provides the steady, organized foundation that allows modern networks to grow to massive scales. Let's zoom in to the microscopic level. What actually happens in the exact moment your phone walks into a new coffee shop and connects to the Wi-Fi? Your phone and the network server engage in a high-speed four-part negotiation. Network engineers call this the DORA process: discover, offer, request, and acknowledge. Looking at this network grid, we see step 1, discover. Because your phone doesn't have an address yet, it shouts out a general broadcast across the entire network, asking if an address manager is listening. Step 2 is the offer. The DHCP server hears that shout, reserves an available IP address from its database, and proposes that specific number back to your phone. Step 3 is the request. Your phone formally accepts the server's proposal, sending a message back to confirm it wants to use that exact address. Finally, step 4 is acknowledge. The server locks the assignment into its records and sends over final details, like where to find the gateway, which is the digital exit door that leads out to the rest of the internet. Discover, offer, request, acknowledge. That complex negotiation is fully completed in the milliseconds it takes for the Wi-Fi icon to light up on your screen. But giving out addresses creates a logistical challenge. Think about an airport terminal. Tens of thousands of devices connect to the network, leave an hour later, and never return. If the network permanently gave away an address to every visitor, the available pool would empty out by lunchtime. To solve this, DHCP does not give addresses away, it rents them. This is managed through a feature called DHCP lease time. This grid represents a finite pool of IP addresses. In a high-traffic environment like a coffee shop, the server assigns very short lease times. As you can see, mobile devices hold on to their address blocks just long enough to browse, and when their timers hit 0, the blocks are immediately returned to the pool for the next customer. Conversely, in a stable corporate office where desktop computers sit on the same desk all year, the server assigns very long leases, sometimes lasting several days. This prevents the network from being clogged with constant rental negotiations. You don't have to worry about getting kicked off the internet mid-task either. Once an active device reaches the halfway point of its lease, it quietly asks the server for an extension, and the timer refreshes. By treating IP addresses as temporary rentals, finite network infrastructure can successfully serve a virtually infinite rotation of users. That works perfectly for a single room, but massive enterprise networks are divided into dozens of separate, isolated departments to keep traffic organized. Routers are designed to act like soundproof walls between these departments. They keep local network chatter contained so that one department's data doesn't slow down the whole company. But this means your phone's initial hello shout is also blocked. It can't reach a DHCP server sitting in a different department. To bridge this gap, we use a DHCP relay agent. This dedicated messenger sits in the local department, catches that trapped shout, and carries it directly through the soundproof wall to the central server on the other side. With relay agents positioned in each department, a single central DHCP server can efficiently manage millions of addresses across an entire global organization. Because DHCP was designed for seamless speed and convenience, it is incredibly trusting. By default, it does not require strict proof of identity when handing out addresses. This is DHCP spoofing. When a device shouts for an address, a malicious server answers first with a fake offer. The device connects, routing all user data directly through the attacker's machine, allowing them to intercept sensitive information. To prevent this, administrators use security settings on their central connection hardware, the boxes where all the network cables meet. These settings act like a digital security guard, making sure only authorized servers are allowed to give out addresses. From the millisecond you open your laptop, a high-speed negotiation takes place. Addresses are broadcast, offered, and acknowledged. Timers are set, leases are monitored, and relay agents bridge the gaps across fast buildings. The next time you connect to a network instantly, you will know exactly what is happening in the background. It is an invisible, automated infrastructure, making sure your data always finds its way home.